Hello students, my name is Ayela Gabre. I am physics teacher. This is grade 12 physics unit 2 two-dimensional motion, lesson 4, Kepler's law of planetary motion and Newton's law of universal gravitation. After the completion of this lesson, you will be state Kepler's 3 laws, apply equations to solve problem related to orbital motion, use the formula of universal gravitation law to describe motion of satellite, apply equations to solve problem related to Newton's law of universal gravitation. Before we are starting to discuss about Kepler's law and Newton's law of universal gravitation, let's revise some points about the rotational motion, because these two laws are concerns about the rotational motion. The rotational motion is the motion of an object or a body in which all particles move in a circular path with a common angular velocity and about a fixed axis. The kinematics of rotational motion describes the relationship among rotational angle or angular position, angular velocity, and angular acceleration and time. Let's start today's lesson about the first part is Kepler's law of planetary motions. Planetary motion is types of curved linear or rotational motion. And the planets orbits the sun due to the gravitational force of the planet exerted by the gravitational force of the sun. The planet exerts a force on the sun and the sun exerts on the planet. This keeps that the satellite or the planets moving around the orbits or around the sun. They maintain their respective distances from the sun due to this force. And the path of the motion is called orbit. Kepler's law also describes how planetary bodies orbit around the sun. Then Kepler discovered 3 empirical laws that accurately describe the motion of a planet around the sun or satellite around any given planet. There are consequences of Newton's law of motion and the laws of gravitational motion, which means the motion of these planets can be studied by the consequence of Kepler's law and Newton's law of universal gravitation. Kepler's first law, sometimes referred as the law of ellipse. Kepler's first law states that all planets move in an elliptical orbit with the sun at one focal point of the ellipse. The planet follows the ellipse in its orbit, meaning that the planet to the sun distance is constantly changing as the planet goes around its orbit. Kepler's second law. Kepler's second law states that a line drawn from the sun to the planet sweeps out equal area in equal time interval. Kepler's second law is sometimes referred to as the law of equal area because it talks about or states about the area swept by equal line with equal area. It also states that the planets do not move with constant speed along their orbit. The velocity will vary when they are moving in their orbits. This is stated or explained by Kepler's second law. Kepler's second law is related to the physical principle known as the conservation of angular momentum. Conservation of angular momentum is the momentum initial is equal to the momentum final, or the change in angular momentum initial is equal to the change in angular momentum final or after the impact. So this Kepler's second law is based on this principle. The point at which planet is nearest to the sun is called perihelion, and the point at which point is greatest or that's larger distance from the sun is known as aphelion. The next one is Kepler's third law. Kepler's third law states that the square of the orbital period to revolve around the sun or around a given satellite of any planet is proportional to the cube of the average distance from the planet to the sun. So mathematically this is given as t square over a cube, that means average distance cube, is equals to constant, which means ks. We have a reason to say that is ks because the sun is taken as the central object. Then where k is this constant, 4 pi square over g gravitational or universal gravitational constant times mass of the sun. T square over A average distance cube is equals to Ks implies that T1 square over A1 average distance cube is equals to T2 because they are proportional, T2 square over A2 cube. If we have two, or if we have asked to compare the time period or the average distance from the sun to the planets, we can use this relation or this expression because the ratio gives us the constant value that is K. If we consider the orbits of a satellite such as a moon around Earth, and the constant has different value, because we have said that the constant value is 4 pi r square over the gravitational constant times mass of the sun. This mass, if it is the central body is Earth, this mass becomes the mass of the Earth. Therefore, the mass of the Earth and the mass of the sun is not equal, then the constant K is not always equal. If it is equal, only when the center is the sun, for all planets is constant. But if we take the Earth is at the central object, K is constant for all satellites that moving around the Earth, which implies that this has a special case for the K is constant. And Kepler's third law equation is valid for both circular and elliptical orbits. Okay, let's see the video that is clarify what we have stated and discuss about the three Kepler's law. Okay, let's see. This one is Kepler's first law. Because if you look at the satellite, it follows an elliptical orbit, which has two phases. Then this one is the major axis and this one is the minor axis, which gives us the elliptical orbit or the elliptical shape. And second law states that the line sweeps equal area can have the equal amount. So this area is equal with this one, this area will equal with this, and so on, because it can cover equal time, equal area. And from this, when the satellite is near to the farthest point, aphelion, it will travel slower, but it is at the perihelion, it will have a larger speed. If you look at clearly, the speed is varying when it is revolving its orbital path. This shows that the Kepler's law is very important to explain the motion of a satellite around the given massive central objects. Or if we take that is the solar system, the central object is that of the sun. Okay, let's do an example concerning this one. Example 1. Think of the planet orbiting the sun. Do all the planets move at the same speed? At which position are the planet's orbital speed is greatest? Explain why. We can answer this question based on the Kepler's law of planetary motion. So the answer for this one is all planet does not revolve with the same speed around the orbit, because the orbit is an elliptical shape. The satellite or the planet near to the sun, for example, if we take that the sun is a central object, the planet is near to the sun, it will have the greater speed. And when the satellite is moving away or as the farther distance from the sun, will have a smaller speed or slower. This is because there is a gravitational force. The gravitational force is greatest when it is near to each other, and it is very weak or small when there is very farther from the object. So this is the answer. The planet near to at perihelion is faster, and at aphelion is slowest. So the cause for that one is the gravitational force. This is because the gravitational force at perihelion is greatest and greater, and at perihelion is smaller. This is the cause for that one. Let's do again the second example. If Saturn is on average 9 times farther from the sun than the Earth, how long it is year in times of Earth year? How many times in terms of? If Saturn is on average 9 times farther from the sun than Earth, how long it takes in year in terms of Earth's year. Let's do the solution. We have a given average distance of Saturn is given as 9 times of average distance of Earth. And time period of the Earth in year is that T of Earth is equals to 1 year. And you can say that the average distance of the Earth as AE. Then the required is what is the time period of the Saturn. We can apply Kepler's third law to find this one. That means T of Earth square over the average distance of Earth cube is equals to the time period of Saturn square over the average distance of Saturn from the Sun cube. So if we solve for the time period of Saturn, Ts square of Saturn is equals to the time period of Earth square times the average distance of Saturn cube over the average distance of Earth cube. Then if we substitute this one, T of Saturn square is equals to T of Earth is 1 year, 1 times T of Saturn is, distance of Saturn is 9 times of distance of the Earth, average distance of the Earth, which means 9 times AE of, or distance of Earth cube over distance of Earth cube. Then this becomes T of Saturn square is equals to, when you cube 9, we get that 81 times 9, that means times A of Earth cube over that of A of Earth cube. This will be cancelled. Then T Saturn square is equals to, I think when we multiply this one, we get that 729. Then T of Saturn now becomes under the square root of 729 years. It can be potentially 27 years. So this is how we can apply or how we can find the time period of a satellite using Kepler's law of planetary motion. So the next topic for today is that Newton's law of universal gravitation. Newton's universal law of gravitation states that every object in the universe attracts every other object with the force that is directed along the line joining them. The force is directly proportional to the product of the mass of that object and inversely proportional to the square of the distance between the two objects. That means the force of gravity, according to Newton's law of universal gravitation, is proportional to that of the product of the two masses, m1 times m2, and inversely proportional to the square of the separation distance r square. Which means if we take that is m1 and if we take m2, this is the distance r, the separation between them. So the force of attraction between these two mass is inversely proportional with the square of the separation. Don't confuse. It is not with r. It is with r square. The square inverse square relation. Then, if we take our Newton have determined that this constant, Newton's gravitational constant, then we can convert this one into equal sign. Then F of G or gravitational force is equals to the universal gravitation times mass 1 mass 2 over r square. This G has a constant value. It is constant 6.67. 3 times 10 raised to minus 11 Newton meter square per kilogram square. The gravitational attraction of the sun provides the centripetal force needed to keep planets in orbit around the sun. Earth's gravity keeps the moon and all types of satellites that are artificial satellites orbit around the Earth because the gravitational force provides a centripetal force. The centripetal force Fc is equals to mv square over r, which is equals to the gravitational force Fg, which means g times m1 m2 over r square. These forces are equal, means in other words, the centripetal force is the gravitational force between two objects. This force is not only on the universal object, it is also between any two masses present, and it is always attractive force. Gravitational force is always attractive force. Okay, let's see Newton's law of universal gravitation. Look, if the mass increases, the force also increases. This arrow indicates that how the size of the force increases. If we make an approach toward them, the forces decreases. Force M1 by M2. The force on M1 by M2 is this force because they are attractive force, and this one is also attract this object toward this the left. Then if we increase the mass, look, if we increase the masses, the force of attraction increases because according to Newton's law of universal gravitation, the force between any two objects is directly proportional to the product of the masses and the distance, inversely proportional to the square of the distance between the two objects. Therefore, if you increase the distance, then the force between them decreases, and if you increase the mass of each object, then the force of attraction between them is increased. So you can clearly look from this video. So this is how we can represent Newton's law of universal gravitation using a video, or how can it. I think you have some information about the Newton's law of universal gravitation from the video. Let's proceed to the next. Let's do examples using that Newton's law of universal gravitation. A 10 kilogram mass and a 100 kilogram mass are 1 meter apart. What is the force of attraction between these two masses? So let's do the solution. Okay, let's solve this problem. Solution. So given M1 is equals to 10 kilogram, M2 is equals to 100 kilogram, and R is given as 1 meter. We can take also G, gravitational constant, as 6.67 times 10 to the power of minus 11 Newton meter square per kilogram square. The required is Fg. What is the gravitational attraction between these two masses? As I have told you previously, any two objects are attract each other because there is a gravitational force. Fg, the gravitational force, is equals to G times M1 M2 over R square. We have the values for each variable. G is 6.67 times 10 to the power of minus 11 Newton meter square per kilogram square, time the two masses are 10. The first mass is 10 kilogram times 100 kilogram over 1 meter square. So meter will be cancelled with meter. Here is I have a kilogram square will be cancelled with the 2 kilogram. Then we can have that 6.67 times 10 to the power of minus 11 times 1000 over 1. The remaining unit is here Newton. Then this becomes final answer 6.67 times 10 to the power of, there is 3 here by the way, it becomes 10 to the power of minus 8 Newton. So this is, look how much is very small. This is the reason why we do not feel the forces between two objects. For example, between me and this board there is an attractive gravitational force, but we do not, I am not feeling that one because the force is very, very small. This is the reason where we do not feel the force of gravity. But if the mass of two objects or either one object is very huge as that of the mass of the earth, we feel that forces. So student, this is the exercise for you. The first exercise is that if the distance between the earth and the sun were half its present value, the number of days in a year would have been A, 64.5, B, 129, C, 182.5, D, 730, days. In day this one. So if the distance between the earth and the sun is half, the number of days could be 129. And second question, if a person has a mass of 60 kilogram, what would be the force of gravitational attraction on him at Earth's surface? At the Earth's surface. That is 600 Newton is the answer. So cross-check your answer with this one. So this is what we have discussed today. So let's summarize what we'll state previous slides. Planetary motion is a type of curvilinear motion, and this is studied by Newton and Kepler. So Kepler forms three laws, that is Kepler's law describes planetary bodies orbits around the sun, and Kepler discovers three empirical laws that accurately describes the motion of planets. And Newton's law of universal gravitation states that the force between any two objects is directly proportional to the product of the mass of each object and inversely proportional with the square of the separation between the objects. So this is for all today. Thank you for your attention. Don't forget practicing the exercise and cross-checking your answer with the given answer key. Thank you very much. Have a nice study.